All right, welcome to an episode of Science with Surback. Today what we're going to do is we're going to introduce the topic of the atoms and talk about the early theories of matter. Now, before we get going, there's a couple of objectives I would like you to be able to meet by the end of this video. So objective number 1 is to compare and contrast the atomic models of Democritus and Dalton. And objective number 2 is to define an atom. The other thing that I want to point out here is that these notes contain the words that you need to fill into your notes. So you'll see the red words that are highlighted in yellow. These are the words that you need to fill in. You need to fill into your notes. So let's go ahead and let's get going with our first slide here. So early on, and this is several thousands of years ago, we had some early thoughts on what things were made of. And so these early philosophers said there's some simple things that we have everything made of. And they said everything's either made of earth, water, air, or fire. Now you have to remember way back when they made this, or way back when they first theorized what items or what matter was actually made of, there was very few tools or very few technologies that scientists could use. So they had to do a lot of speculating. They had to do a lot of guessing. They also believed that matter could be endlessly divided. Now, this was revised not very far away from these early philosophers. So we'll change slides here and we'll go to Democritus. Now, Democritus, he existed almost 2,500 years ago, and Democritus was the first person to say, all right, at some point, these matter, these things cannot be divided anymore. Or if they do get divided, they're going to lose their identity. They're going to become something else. He was also very instrumental in saying, hey, once you get down to that point where atoms cannot be further and further divided, they're going to lose those identities, and he named those atomos. And we'll see that term throughout this chapter when we talk about the structure of the atom. He also said, all right, matter cannot be created or destroyed. Now, one thing that was actually lacking here was that evidence. These things that Democritus has pointed out was actually very true. They just didn't have the technologies or tools or evidence to prove or disprove Democritus. So, not very far after Democritus came Aristotle. And actually, they were about the same time. They existed about the same time. You can see there that timeline. And Aristotle, he was a much more famous philosopher. And he said, no way, Democritus, you are not right. He said, okay, even if you were remotely right, how can you explain this empty space that is in between these atoms? And because Aristotle said this, his word held true. So what happened here is because Aristotle challenged the thoughts of Democritus, they thought for almost 2,000 years that we had these simple elements or these simple composure that matter was made up of. Now, in the late 1700s, early 1800s, we have a big revolution in science and we have a big revolution in chemistry. So we go ahead and we change towards John Dalton. So John Dalton was a teacher in England, and he looked at Democritus' theory that he said, and he said, those are some pretty good thoughts. What I'm going to do is not only am I going to expand on those thoughts, but I'm going to prove it one way or another. And so the way in which he proved this theory to be right or wrong is he started to conduct research. Now, remember, up until this point, there hasn't been a whole lot of documented research in the scientific field. And without that documented proof, you can not prove or disprove what is going on here. So let's go ahead, let's get straight to what Dalton proposed after his several experiments. Okay? So Dalton, he does these experiments to try to expand on what Democritus is saying, and he says, all right, matter is composed of these small pieces or small particles called atoms. And this is directly what he got from Democritus's theory. He also said, which we'll correct here in a second, that atoms of a similar element are identical and atoms of other elements are different. Now, again, we are going to come back to this, and so I'm going to star point 2 here. And we'll move on to point 3. So atoms cannot be created, destroyed, or divided into smaller pieces. All right? So again, this was taking Democritus's theory and expanding on it. And then he also said, hey, in a chemical reaction, atoms cannot be destroyed, but what happens is that these atoms separate from each other, they get rearranged, and they combine in different forms. So, with this point number 2, I said we would circle back to it, and it says atoms of a similar element are identical. Now, this point right here, I'm going to pause the video and say this. This point right here was proven incorrect, and it's because of these things called isotopes. All right, so again, point number 2 was proven incorrect because of isotopes. Now, another thing I don't have on here that I want to add is that Dalton said atoms cannot be divided any further. So again, Dalton also said that atoms are indivisible or cannot be divided. This was proven incorrect because they found smaller particles, which we'll learn about later on. And those smaller particles are things such as protons, neutrons, and electrons. Okay, so let's expand on Dalton's theory a little bit more. So we have these statements here that now have a lot of backing in them, and they have a lot of backing, or they have a lot of support because they have this documented research. And so let's go ahead, let's take a look at what this documented research was that Dalton conducted. So in Dalton's research here, he did numerous detailed experiments based on observation, so what he saw, on chemical reactions. So everything that we just stated on that previous slide, Dalton didn't just think about and write down. He actually had proven documentation of what was going on. So with this, with these observations, he explains the conservation of mass. So essentially what he did in his experiment was that he ran the reaction, and at the end of the reaction, the mass was the same as the beginning of the reaction. So there was no loss of mass, and if there was, Dalton could figure out, well, where did it go? Did it turn into a gas? Did it evaporate? So on and so on and so forth, he could figure out. So the major thing here of why Dalton's theory worked so well was that he had this evidence. All right? So this evidence gives scientists that backing or that understanding of what he says is true because he can back it up with physical proof. However, with all good scientific research, there are some additional questions that are raised. So now they establish, okay, matter is composed of these really small particles of atoms, but what do these atoms look like? If they're so small, how can we even do more research? And to expand on that, we want to know, okay, how are atoms shaped? And then the major thing here is this. We have empty space, and how can we prove or disprove that there's empty space between atoms and between pieces of matter. And so there was a lot more questions raised by this significant research that Dalton did. Now, Dalton proved a lot through his reactions and through his observations that were documented, but now we have even more work to get through to try to explain some of these things with atoms and of matter. So let's go ahead, let's take a quick look into an atom, because that's what we're going to be looking at in detail this chapter. And so an atom is defined as the smallest particle of an element that retains the properties of the element. So I have an example here, and this example is if we had a pure gold ring, and we took the ring and we cut it in half. Well, that half of that ring would still be gold, and we would know that. We could do experiments on that. And then we could take that half a ring and cut that in half. Well, that quarter now of that ring would still be gold, and we could cut it in half, and we could cut it in half, and we could cut it in half, and cut it in half until we got down to a single atom. So let's say we had some specialized tool that could keep cutting that gold ring in half and half and half again until we got down to a single atom of gold. Now, at that point, we still have gold. We still have all the properties of gold, even though we have a single atom of gold. However, if we slice that single gold atom just one more time, it would no longer be gold. We would take some of the pieces and parts away that would be unique to have to gold. So, what we have to remember here is this. Atoms are the smallest particles of an element that retains the properties. Okay? So, we'll get to that here in a second. Now, just to wrap your mind around an atom, I want you to identify the size or have some type of visualization for the size of an atom. So atoms are very, very, very small. We have the measurements here, but that doesn't really mean much to you or me. The major thing here is this point we have written down. If we take a pure copper penny, so the same penny that you'd pay for things, in that copper penny, so penny containing only copper, there would be a significant number of atoms of copper in that penny. You can see all these zeros. I'm not even going to try to list out or go through that number there. That is how many atoms are in a penny. So when you think about this, atoms are very, very, very small. And so this, at this time, remember we're in the late 1700s, early 1800s, it was difficult to do experiments on something that was so small. Now, technology has advanced and it's gotten better and better and better, and we're able to see smaller and smaller things. And one thing that helps us identify an atom is a scanning tunneling microscope. And so again, that's just an instrument used to identify and show and do experiments on these atoms. Now, the last thing that I want you to visualize is this. Let's say we had a pencil, and we took the pencil, and I got a pencil example here, and we said the tip, just the tip of the pencil, was what we call the center, the nucleus of the atom. And we put that pencil right in the middle of this huge soccer stadium or football stadium. The outside of the atom would be moving around that center relative to the size of that football stadium. So the major point here is, hey, we're going to have some empty space in these atoms, and we'll get to that later and help explain why that is. All right, so I hope you have enjoyed this section of notes. And as always, if you have not done so already, make sure you subscribe.